So as Hiroshi said, we started talking about this conference well before September 14th. And somewhere along the way, I knew more than the other committee members, but I couldn't tell them anything. So you notice the title of my talk is not very revealing. And the program, though, I pushed in certain ways that the program would accommodate what I knew that the committee didn't know, and I think I didn't reveal too much. Anyway, there's going to be several talks that will address the question of, address the discovery that we've made in gravitational waves. Mine will be pretty much an introduction. Alessandra Buonanno tomorrow will kind of continue where I'm going to leave off and talk more about the actual tests of general relativity that we can do now and will do in the future, and especially the astrophysics as well that we can do. I'm going to take you through LIGO and the discovery itself and the evidence we have and what it means. And then she'll pick up tomorrow on that. There's also the next talk on the sociology. We've had a sociologist, Harry Collins, who's followed us from the beginning. I don't know what he's going to say, but that'll be an interesting complement as well. Okay. So I'll start, maybe not historically, but at least chronologically, that 1.2 billion years ago, two objects, black holes in the distant universe, were now in the distant universe, coalesced into a single black hole. It's the thing that we've observed. This picture, which is from a supercomputer simulation, is slowed down by a factor of, 100 or so. The whole event takes place in a quarter of a second. The objects are going at relativistic speeds in real life, and you're seeing a slowed down version of the coalescence. 100 years ago, of course, which is what this conference is about, Einstein predicted that there would be gravitational waves through the theory of general relativity. And 50 years ago, the subject we heard yesterday in the Bacon lecture about the intervening 50 years, maybe. But 50 years ago, the subject of trying to observe gravitational waves began with Joe Weber. And Joe Weber, this is a picture of him and the kind of device that he used to try to detect gravitational waves, which was a resonant aluminum bar with detectors along the middle, which you can see. And that was the first gravitational wave experiments which used them during the 1960s. They're a cylinder of aluminum. Each end basically acts like what we call test masses in the present interferometers. And the center is like a spring. And PZTs that are around the midline send an electrical signal to an amplifier. So that's what was the technique. That technique was refined over many years. And we have, in what I'll show for LIGO, several things, just I'll pick what I think are the key ones. A certain legacy in the way we do a rather different method from Weber's work. The first is that he did sensitivity calculations of the noise that limits the measurements, something we spent a lot of effort on in LIGO. The second is that he developed the system of having two detectors separated from each other and doing coincidence to do background rejection. A second thing that we do, having two detectors. And the third is the way we measure how probable the event is to just have background, and that is to do time slices of the background estimation. All three of those that are important in what we present today come from that legacy that Weber had. The bars, though, as a technique, are limited in sensitivity. They're limited because they're a resonant bar. They ding at a certain frequency. And they're limited in width, although there's an attempt to make them as broad as possible. And they're also limited in how long you can make them, which determines how large the signal is, because what we measure really experimentally is a change of length over a length. And so the longer it is, the easier that is. The resonant bars continued after Weber until we were basically are running, maybe even into the time we've been running interferometers, by going into a regime where they cooled the bars. And this is follow-up groups after Weber. And one of Weber's students, Robert Forward, was the first person in America, at least, to explore the idea of using interferometers to measure gravitational waves. So there's a long positive legacy that comes from Weber. There's also a negative part, and that is he claimed detection first in 1969. This is the picture from a phys rev letter that he had, the signal seen that he thought was a signal seen at University of Maryland and at Argonne Lab, 2 different detectors. This proved to be non-detection, but a claimed detection, and he claimed several more during his career. So there's both a plus and minus to Weber's background. 30 years ago was the indirect detection of gravitational waves, in the sense that what was observed was the effect of having gravitational waves in a particular system. The system was a binary neutron star pair. They were observing a binary neutron star that had a frequency of 17 times per second, and that neutron star they discovered was modulated about every 8 hours, and the interpretation was that there was a second neutron star going around. So they studied this pair of neutron stars called PSR 1913 plus 16, and basically measured how much due to the radiation, the period speeded up from the 8 hours. And the picture on the right is the graph of that speed up over a period of about 20 years, of about 20 seconds out of the roughly 8 hours of the period. The errors, the data points are shown with errors, little dots, and the line is not a fit, but a calculation using the parameters of the system to calculate how much radiation or how much speed up there should be, because some of the radiation is causing the slow in spiral of this system. Then 6 months ago, basically this picture is a result from LIGO, which I'll come back to. We saw coming up from the southern hemisphere what was the gravitational wave signal from the system that was 1.2 billion light years away. And on September 14th in Livingston, we observed this signal, which I'll interpret for you as we go along, but the signal is basically the chirp signal that we call the chirp signal, which is the in spiral, the merging into a single black hole, and a ring down after that, which I'll describe. 7 milliseconds later, we saw the same thing in Hanford. So the 2 signals, one in Livingston, one in Hanford, by eye, look very much alike. They're separated by 7 milliseconds. There's a shift in direction because one is upside down from the other. But again, drawn in advance is the picture or the prediction from general relativity, which I'll come back to, the little line that you can see. We worked on this observation from September 14th until February 11th, when it was published in Phys Rev Letters. And the first plot in the paper is shown here, which is the maybe massaged plot of what I showed you before, the theory, the errors, and a time frequency plot. I'll dissect these for you as we go along so you can understand them and what we've actually seen somewhat better. But let me go back first. So let's go back to what we're really doing in detecting gravitational waves, starting from the concept. So the first thing, as we know, that happened is that Newton's theory of gravity has been supplanted by Einstein. The key difference is that space and time are separated in Newton's theory, which was successful for everything that was measured to the days that Einstein developed his theory, except the period of Mercury around the sun, which had a very small difference. And in 1915, Einstein put forward his theory of general relativity, which unifies space and time in a four-dimensional space-time. So in Newton's theory of gravity, the force, as we know, depends on the distance between massive objects. And there's a feature that is immediately not what we need, and that is instantaneous action at a distance. If one of the objects moves, the other one feels it immediately. While in Einstein's gravity, there's time-dependent gravitational fields propagate like light waves, proportional to the quadrupole moment, and they propagate at the speed of light, the one speed that exists in the whole problem. I'm just going to have one slide to illustrate for you what are gravitational waves, how do they come out of the theory. I've picked a particular way to write the formula from general relativity of the radiation, and it's what's called the Minkowski metric. And if I write it in this way, then the thing that we're going to measure is called the strain, is this little h mu nu. And in the end, I'm going to talk about what that is experimentally. If we look at it in the weak field limit, which is not the limit that the observations made in, but for the purpose of this talk, I want to use that. Then we get a familiar equation on the right. It's basically the wave equation, just like we have in electromagnetism. And the strain, h mu nu, takes the form, like in E&M, of a plane wave, propagating at the speed of light. And it has two polarizations, as is shown on the right. And that's because gravity is spin 2. That there's that's a fact that's there also in electromagnetism, but the fact that gravity is spin 2 makes the two at an angle of 45 degrees from each other rather than 90 degrees from each other. We can resolve these polarizations in the detectors that are being used for gravitational waves, but we have no information on it, and I'll point out why for the first observations that we've made. There are several sources, there's lots of sources of gravitational waves that people can look at, but on the Earth's surface, the primary sources that we have available, I've shown in this slide: coalescing binary systems, like the one we've observed, a burst that might come from something like a supernova, a stochastic background from the early universe, or a spinning neutron stars, which would be a continuous source. I'm only going to talk about the one that we've observed, coalescing binary systems, and in particular, coalescing binary systems that come from two black holes. So the basic picture, which is like the one I showed on the very first slide, is a history that shows three things. First, the in-spiral of two objects coming together, which is what we call the chirp signal. The merger itself, which is very interesting from the point of view of general relativity and strong field studies. And finally, when it becomes one object, the ring down. And we'll see what that looks like in what we have. This is just a picture of putting in roughly the parameters that we've observed and the strength of this little h. H is 10 to the minus 21, roughly. And I'll show what that means in a detector in a minute. As gravitational waves come, then, from this object in deep space and come through the Earth, the effect they have is to stretch and squash at the frequency of the gravitational wave at that moment, the coordinates, the orthogonal coordinates, so that what's happening is that the coordinate system is getting squashed and stretched, and the measuring device, which we're going to use, an interferometer, also gets squashed and squeezed. So one leg gets longer while the other leg gets shorter, and then it goes back to the other way, and that is at the frequency that the gravitational wave is propagating through the detector. So it turns out that this is ideal for something like an interferometer, and that's why an interferometer is such a good choice. Interferometers measure very accurately the difference between two lengths, which is always easier to do than measure the absolute accuracy of something. And we're limited by just how well we can make the interferometer itself, and I'm going to try to show you some of that. So in order to do this, in order to measure delta L over L as accurately as we can, we make the legs as long as we can. And so LIGO has 4-kilometer long legs. One leg is shown here, and the other leg goes off to the side. And this is one of our two sites, which is in the state of Louisiana, a little town nearby called Livingston, Louisiana. And the other one, you notice this one is in a pine forest. Also along the side, on the right side, you can see that essentially at the Earth's surface, it's all water. So as soon as we excavate to put LIGO in, we get a channel of water on the right, which collected everything from fish to alligators quickly. And the site in Hanford is quite different. It's high desert with much more stable ground. But for the purpose of today and for essentially they're identical instruments. So we have two identical instruments that are separated by 3,000 kilometers. So like the idea that was done by Weber, we have two separate detectors where we can compare the signals. The 3,000 kilometers at the speed of light is 10 milliseconds. So depending on the orientation of a source that comes through our detectors, they could come at exactly the same time, or if one comes from the right to the left or the left to the right, it's plus or minus 10 milliseconds. In searching our data to be able to encompass that, we use plus or minus 15 milliseconds. But basically, that's it. You can see from the picture that Caltech and MIT are at one angle, and that Hanford and Livingston are at a different one. The history there is that I think in the early days, the hope was that there'd be a California site, maybe near the Edwards Air Force Base, and a site in southern Maine near MIT. But when it went to the government to get funded, what came out was a site in Washington and a site in Louisiana. So then construction began. This is an early picture of LIGO when construction began. And even at this point, we had to make a scientific decision. And the decision was the following, that these two legs that are shown, should they be parallel, taking into account the curvature of the Earth, parallel to the ones in Louisiana, or at 45 degrees to the ones in Louisiana? If they're at 45 degrees to the ones in Louisiana, we have information. We would, in principle, have information that enables us to disentangle the two polarizations that I talked about. So that's the reason you might do it that way. If you did them parallel to each other, then we don't have that information, but we can demand that the signal that we detect in detail at Livingston looks the same as the one in Hanford, taking into account the small differences in the curvature of the Earth. We decided to make them parallel to each other. So the data that I'll show you is parallel. One's upside down from the other, but they're parallel to each other. That choice was made in order to since we had never detected gravitational waves, to have the best confidence we could possibly have that we actually detected gravitational waves. The information that I'll show you later would look quite different, probably, depending on the polarization. If we had had them at 45 degrees from each other, we couldn't have demanded that they look the same in from the two sites. So we picked them parallel. One of the reasons to do that also was that we're not alone in the world and there'll be other detectors. And in practice, one was being built in parallel in time with ours. It's a little bit later. And that's near Pisa in Italy, and it's the third detector, and the curvature of the Earth and its orientation helps us, in principle, to be able in the future to resolve the polarization of the gravitational wave. This is then the beginning of construction of the device itself. On the upper left is the starting of the building of a beam pipe. You know that a laser beam is tiny. And the beam pipe is 1.2 meters in diameter. The reason we make it 1.2 meters in diameter is several reasons, but one is that the inside of the beam pipe is our laboratory. So in thinking toward the future, or in running more than one interferometer, we have a lot of space to put more interferometers together. So the foresight there is to make a big pipe in order to have the ability to develop whatever we want to do in the future. Secondly, by having the walls of the pipe far from the beam of the laser beam, then we can more easily handle any background that comes from scattering off of residual molecules that are in this vacuum. So the pipe, which is shown in the bottom right, is 4 kilometers long. We made it in sections that are welded in place and with a minimal covering to protect us from the weather around the whole device. So that's our basic arms that the interferometer sends the light down, and there are a few glitches on the way. I show one picture to give you a sense of how we approach then the central part of the interferometer. What you see are great big chambers, but with a lot of ports and places where you can take things off, and 2 items that I want to point out on the 2 sides. And the idea here was to create a place where we put the principal things, the optics, and the laser is not shown here, but the laser in a way that we can continue to access and upgrade and change things as we learn more about how to do the interferometry. We have 2 big what are called gate valves here and here, which were put in to close off the long vacuum pipes and not have to bring them up to air if we want to work and change or develop the optics that are inside. I'll show you that evolution of the optics as I go along. But the idea at the beginning is we knew how to build something to start with. We were developing the ideas of how to build things that would be more sensitive, and we will still in the future from now develop things that are on the drawing board now that we can install in the same infrastructure. So this infrastructure, we said from the beginning, should be good for anything we can dream up for 30 years. That was the idea. It's now 22 years old. The basic infrastructure has first what you have in your automobile, basically passive seismic isolation, which we used from the beginning, which are springs and masses. They're special springs. They have a squishiness that are adapted to us, and basically make a table that we can work on and put our optics that's as stable as we can make it, until we add extra features, which I'll talk about later. So for the first part of LIGO, we just put in the best seismic passive system that we could, and put mirrors that you need to make this interferometer, and the mirrors themselves become the test masses that we want to see move in order to measure gravitational waves. And basically this is the simple features at the beginning. We hung it with the first test masses with a piano wire, and the test masses themselves are made out of fused silica. And the wire itself is 0.31 millimeter standard piano wire. And within that, there's some fundamental, I point out one, there's fundamental frequencies where any mechanical system you make is going to resonate. So when I show the sensitivity curves, you'll see these little things that go up. Those are almost all known and stable, and because of the construction of the system. And we've identified most of them. About the time we were finishing constructing the initial LIGO, we decided for the long term that having a broader collaboration, both for technical strength and for scientific input and to help with data analysis and everything else, we should open up the collaboration. We made what's called the LIGO Scientific Collaboration, and most of the communication you've heard about the discovery comes directly from the LIGO Scientific Collaboration, which now has about 1,000 scientists from around the world. So let me talk a little bit about the interferometer itself and show you how that works. as I said, we use a laser to measure the relative lengths of the two orthogonal arms, and one of them is going to get shorter and one of them longer, and vice versa, at the frequency of the gravitational wave. The masses that you see here are mirrors or suspended, which keeps them isolated from the Earth. And the length that we want to measure is to compare the length of these two arms and see if they're different. What we do is let the light go down both arms, split the beam, let the light go down both arms, and set it so they cancel each other, basically. And then the photodiode, in the simplest configuration, is dark, and if one arm gets longer than the other, it becomes lighter. So that's the so-called interference pattern that we measure. The arms in LIGO, as you saw in the picture, are 4 kilometers long, and they measure a difference in length of 1 part in 10 to the 21. We're actually better than that, maybe. Or 10 to the minus 18 meters, a small fraction of the size of a proton, which is amazing, and that's done because we have so many photons. We measure it many, many times. As I said, the masses are suspended. The length is that. Now, this is what limits us, and this is what I want to go through, and then you'll see what enables us and maybe what's taken us 22 years. We started the construction in 1994, and we're continually battling the fact that something limits our ability to make this as sensitive as possible to measure the difference in the lengths of these two arms. The first thing, and I showed you the vacuum pipe, is just residual gas. So any residual gas has molecules in the vacuum pipes, and the laser beam scatters off of that. If it can find, it could scatter back with a different length off the sides, say, back, hit the mirrors and come back and give you some light that is not in phase with the original light. So residual gas scattering is an issue. The wavelength of the laser itself and the amplitude fluctuations. Lasers, as stable as they are, aren't stable enough. So we do more to stabilize the laser for both wavelength and amplitude fluctuations. And again, that can be a limiting feature in the whole thing. Third one is the shaking of the Earth, just the seismic noise. The test masses, even though we're hanging them in one way or the other as suspended test masses, the thing you hang it from still is going to be shaking with the Earth. And that, I'll show you in a graph in a minute, is something that we have to contend with. The next one is the fact that we use test masses for now at room temperature. People are working on, especially in Japan, on making a next generation interferometer that runs at cryogenic temperatures where the noise will be less, but basically the noise or the thermal or Brownian motion of the atoms inside the test mass limit us. And lastly, I'll point out something that we haven't hit yet, but is the kind of limit that we are dealing with, and that is that if we keep raising the power of the laser and have enough power, we put pressure on the mirrors eventually so that there's a trade-off in having enough photons and having radiation pressure issues on the mirrors. So these are basically a set of backgrounds. They are shown here on a plot where the left-hand axis is this strain, basically. This is the 10 to the minus 21 shown here. This is just a characteristic. At the low frequencies, we're limited by seismic background. That falls its frequency to the 4th power, so it's very steep, and it doesn't bother us when we get to higher frequencies, but it bothers us at the lowest frequencies. At the highest frequencies, we're limited by what's called shot noise, which is basically how many photons you have. As an ex-particle physicist, we would call it photostatistics, but it's basically the limit due to how many photons you have in the system. And at intermediate frequencies, we're limited by some sort of motion of the atoms, thermal noise. This already is a difficult problem experimentally because any experiment I've ever worked on before, you have one background and you try to beat it down. But here we have 3 different ones in 3 different regimes. And so these we have to take care of. And lurking below is a whole bunch of other ones that we have to deal with, whether it's the gas and keeping the vacuum good enough, or the fact that there's other backgrounds which are shown, and they're not all shown on this graph. So, we attack this problem kind of in steps. First, as I said, the vacuum chambers themselves, this is a schematic view of them, have built in a passive isolation system in order to reduce the backgrounds that we have from seismic motion. We reduce the in-band seismic motion by 4 to 6 orders of magnitude. We compensate for what's called the microseism, the very low frequency noise, by about a factor of 10. And we even take care of things like the Earth's tides, that is the moon going over the Earth and changing things. This is the original optics. I'll show you the new optics in a minute, which are incredibly good optics. So we make a test mass, but it's made from fused silica. When you look at it, you see right through it here, and that's because it is to the eye and the visible light, it just transmits it. It has a 30-layer coating, dielectric coating on it, that scatters the light back or reflects it if it's at the wavelength, which is 1024 nanometers of the laser itself. The surface, I gave some numbers here, but the surface quality is as good as the best optics for telescopes. So we use very, very good optics. And we've made it bigger and better test masses for the new version of LIGO, the advanced version. This is the data, the last thing I'll show you on the original LIGO. This is the data from our last official test run. We had one after, official data run. We had one after this. First, you can see that what I said before are these various resonances. You can ignore those. They're very narrow. We notch them out. We know what they are. So what's to look at is just this shape here, which looks like the shape I showed you. High frequencies is shot noise, middle is thermal noise, and the low one is seismic noise. And below, I'm not going to go through it, of course, but all these different colored lines are our knowledge of all the different backgrounds that are lurking below us. So that was where we stood at the end of our initial LIGO. A lot of the information empirical from what we'd run into, but I didn't show it on here. But basically, except for at the lowest frequencies, we were pretty much at the design that we had promised the NSF in 1994. We got a little bit better. We had one extra run where we put in some new features and did a little bit better at high frequencies. This is the original design, at which I said we didn't quite reach low frequencies for initial LIGO. What's called advanced LIGO and what has been used to make the observation that I'll show in a few minutes is an ambitious attempt which we started developing in the labs in 1999 when we finished constructing the initial LIGO, the elements that would allow us or enable us to improve the sensitivity a factor of 10. Improving the sensitivity a factor of 10, the thing we call the sensitivity, improves for us how far out we look in the universe a factor of 10. The strain tells us how far out we look. The number of systems, of course, go as the cube of that because the volume increases as the cube. So this is an enormous improvement. Going from here, if we can do it, down to here is a factor of 10 in sensitivity, but a factor of 1,000 in rate where we're struggling to try to make detections. Just because we have 3 different backgrounds, there's really 3 areas we had to attack. One is to make a better system of getting rid of the shaking of the Earth, seismic isolation. A second is to make a system that's quieter due to the thermal backgrounds by using better test masses and suspensions. And lastly, to use a higher power laser. All of those were developed, as I say, in the early part of 10 or 15 years ago. We proposed it to the NSF. It was funded 10 years ago, 10 years ago, and then we started constructing it 5-6 years ago, I guess. This I won't go through in detail are really the boxes of the main improvements, but let me just mention a couple. So this basically compares what we did and measured with initial LIGO with what we improved in advanced LIGO. Some dramatic improvements. A 10-watt laser becomes a 180-watt laser. And equivalently, in the interferometer where we capture the light and resonate it and hold it in the arms to build it up, there's 700 kilowatts of power in the arms compared to 10 kilowatts of power. The mirror is 4 times heavier. We have different kind of optics, optics for the interferometry, and we have better seismic performance, especially at low frequency, which was crucial for this measurement, and a totally different kind of suspension system. So let me just quickly show you a little bit of that. This is the laser, which will be able to go up to 20 times the power of our original laser, and is a lot more complicated than this little pointer that I'm using. As you can see, we have both a high power laser and one that's stabilized to tremendous accuracy. So that's the new laser. It was developed for us by our collaborators in Hanover, Germany, and built commercially by Laser Centrum in Hanover. It's got all the stabilization that I said. This is the optics shown on the side, so you can't look through it, but it's 4 times bigger than the other optic. It's very, very accurately made. It's been hard for industry to make these optics well enough. There's only one place in the world that seems capable. And those have been installed and have improved us by having much heavier test masses. The third thing is to isolate asbestos in the suspensions from the Earth. And here we've gone to a multiple pendulum system instead of just a single wire that holds the test masses. The multiple system allows us to move any electronics or anything off of the test mass itself, let it be perfect. Shaking the top doesn't go down to the bottom as easily, and we can control things from above if we're good enough. That took many years to develop. It was developed for us in Glasgow, Scotland, by our collaborating group there, and we've installed it in LIGO. This is a picture of it installed. And lastly, we added to a passive isolation system, a system that has feedback and is actively isolating us from the Earth. And you can't see the details here, but you can see it. Okay, so we turned on about a year or so ago, and by last September, we were at the curve that's shown here. So up here is the original best graph that we have for our previous running in LIGO. We were able in September, there's 2 lines here, one for Hanford, one for Livingston, and our design is down here. Rather than continue all the way down to the design, our strategy has been, because of the fact that everything gains as the cube, that if we get a factor of 2 or more improvement, we might as well take new data because it's almost a factor of 10 or so improvement in our sensitivity. And so we're working in a strategy where we're going in steps down to the line here. So the fact that we're here is because we haven't yet put in all the features in detail. This improvement here is about a factor of 3 at high frequencies and more at low frequencies. And it's these frequencies down here that are crucial for the discovery that we made. So the improvement was very good at the low frequencies, and in fact, so much different than our original detector that we couldn't have made this observation with the earlier detector. So that's why we didn't see it in years of running before. This just shows another feature of the stability. How do we measure the sensitivity at any given time of this device? We do it by using calculations of how sensitive we are to what we thought would be the first source that we would detect, which is neutron star binary inspirals, the same kind of system that was seen by Hulse-Taylor, and but seeing them in their last merger phase. And we calculate how far out we can see. The number here is about 70 megaparsecs. So that was about 3.5 or 4 times better than when we ran an initial LIGO. And what I'm showing, the reason I'm showing this is to show stability. You turn on these things, but you've got swinging pendula, and you so-called lock it on a fringe, and sometimes it drops out. So by the time we were running in September, about half of the calendar time, we had both detectors running. The other half of the time, one of them had dropped out and had to be brought back in. When we were running an initial LIGO, we were much higher than that, and we will be here once we learn how to use it better. This is the conditions then that we had when we started the run last September. We started the run last September with 100 kilowatts of circulating beam, sensitivity that's shown here, and the two detectors almost identical to each other, and still running at low power on the laser, 20 watts. So last September, we were in the final stages of preparing for the advanced LIGO running, and the very, very, very last step we have is what we call an engineering run. And that's not engineering in the sense of making all the last changes, but basically making sure that we're satisfied with all the parameters before we freeze them, because once we start running, we don't want to change anything because they have to be frozen. So even though it's called an engineering run, it's actually the same as a data run. We just didn't qualify it at that moment. We saw on September 14th in the middle of the night the signal that I'll show you. We identified that signal in our computers and data analysis about 3 minutes later. And we responded immediately, almost immediately, by starting the data run officially, in other words, freezing the parameters that we had. And in order, because I'll tell you how in a minute, in order to know whether this could be just a background signal, we needed to take more data because we had just started. So we needed to take what was 16 live days of data in order to be able to measure background levels. I'll show you how in a minute. 16 live days of data took us a little over a month because, as I showed you, we basically are in coincidence only about half the time right now. And we reported on that data in that physical review letter that I showed you. The last kind of footnote is that the data run continued until January 12th, so we have 3 times more data than we've reported, and we'll soon report on the rest of the data. So there's data to come that's already in the box, basically, that we're working on, but I won't talk about that today. Okay, so let's look at this picture a little bit, and let me dissect it for you. The top 2 graphs, the 2 are Hanford and Livingston, so we always compare one with the other. The top one is the data bandpass filtered between 35 and 350 hertz, the area that this signal appears in, and slid, the time difference with them, between them is 6.9 milliseconds between Livingston and Hanford, which tells us that it came up through the Earth in a particular direction that hit Livingston before it hit Hanford. The second row is the calculated gravitational wave strain using numerical relativity waveforms for the quoted parameters in our paper, which are the ones that fit best the data that's shown there. And the third line for experimentalists and for data analysts is an important line which shows the residuals, or the difference between the calculations in the second row and the data in the first row. And so that shows you kind of the error at any given point and why they're jagged and don't follow each other immediately. The bottom one is qualitative, but it basically shows you what's happening, and that is that as for about a quarter of a second, there's a signal. That signal was shown as time versus frequency, that signal increases in frequency very rapidly in this banana-like shape in both detectors, in the so-called chirp, which I'm not going to play for you as a sound, but you know. Okay, the second figure in our paper shows a little bit more. I think the bottom part of it is the most revealing. The top shows you these 3 phases that I talked about: the in-spiral, the merger, and the in-spiral getting closer together and going faster, the merger, and then finally a single object that rings down. And so we see the merger, finally this more complicated part, that's the in-spiral, the merger, and then the ring down here. The bottom graph basically shows you what we believe is happening to give that, and that is on the left side you see the velocity, and following the one that's the velocity of the 2 objects are increasing with time, but notice they're highly relativistic. They're half the speed of light or even more by the time they merge. So we have two objects that are not just going around each other, but are going around each other at relativistic velocities, merging and merging faster. The second is that the two objects are separated by a distance that is only, turns out, a few hundred kilometers. So we have two heavy objects, 30 times roughly the mass of the sun, going around each other, separated by only a few hundred kilometers and going at relativistic velocities. So they have to be very compact objects to do that, obviously. And that's the qualitative argument. There's other arguments that why they have to be black holes, the only solution that we know that could satisfy this. In order to search for them and to see them, this is the technique that's used. We use two different techniques, one that's less biased than the other, but the best one is the one where we're looking for binary coalescence, what we have. And so that's the one I'll show because I don't have time for both. So we actually search between 1 and 99 solar masses, and we look at the different possible spins of the objects. To do that, we take waveforms that are calculated using general relativity. These waveforms for the kind of source that we've seen have only been developed in the last decade. And in order to cover that whole space, we use actually 250,000 waveforms to cover any piece of this data that we take. And that may make you wonder whether we would see accidentally some thing because we have so many different ones that we do. But we actually have a way to test that, and we do that. We then use what's called a match filter. We look at each waveform that we calculate, we match it with the data itself, and calculate how well it fits, and have a quadrature sum of that from the two sites so that we get an overall fit. And we measure the background by taking the time slices that we have and looking for every time slice at all the other time slices that are out of time, that couldn't have been something going at relativistic speeds. And the total number of time slices that we use are equivalent to sitting there and measuring for 608,000 years, which is a lot, and taking into account the ambiguities and certain things that we have to take into account, we reduce that to once every 203,000 years, a conservative number, which is equivalent to the magic number that's used in astronomy and in physics often for whether something's statistically significant, 5 sigma. So that's equivalent to 5 sigma. That's a limit because we're better than 5 sigma if we wanted to take more data. We only did these 16 live days. This is then the key plot that shows the statistical significance. And what you see here is the number of events. These are the events that have this, the higher this way, the higher statistical significance the event has by comparing the two sites and the templates. And so they come down here. This is one event here, one event here, and then the event that we reported out here. What's shown in the lines here is the result of this time shifting of the backgrounds, and we see that we get nothing as large as this signal that was in time. So the largest signal that we saw in each of the detectors was the one that came at the same time. And all of these here that are here are basically the right signal in one of the detectors against background in the other detector. Finally, we look at the second event here. Oh, if you go up from here, this is the 5.1 sigma. The second event, which is here, we looked at also carefully, both in terms of what it looks like in physics features and whether it's statistically significant. To do that, we eliminated this event, and we get the curve that goes down here. And if you take and look where that is, it actually ends up being just somewhere between 2 and 3 sigma. So it's 2 sigma. That's not considered statistically significant, so we don't claim it as an event, although its features look very much like a real event, which it could be, but we don't have the statistical significance to call it an event. Next, and Alessandra will show much more, and I just want to give you the key features, and then I'll be done. The shape that we have the waveform that we get reveals all the detailed important features of the event itself. I've written the chirp mass formula here. I'm not going to go through it. The next orders allow for measuring mass ratios and spins, and we've basically fit this to the data. When we fit it to the data, and that's the formulas that we use, we get the following key features. And as I say, Alessandro will go through the implications of these more tomorrow. First, probably the most amazing thing is that in a quarter of a second, this object radiated gravitational radiation equivalent to 3 solar masses in a quarter of a second, by far the biggest object in the radiation in the whole universe. The total system reached a peak energy of 3.6 10 to the 56 ergs, and we could put a limit on the spin, that it's less than 0.7. It was 2 objects, one object 36 solar masses, the other 29 solar masses. The final addition comes out 62, with air shown here, which we also get from the fitting, with 3 solar masses carried away. And the spin is shown here. The distance is about 400 megaparsecs, or 1.2 billion light years away. Just some near final comments. So what are our kind of key conclusions before Alessandro walks you through more? First, that stellar black holes exist and are heavy, and there are heavy ones. We didn't know before that there were stellar black holes as heavy as 20 or 30 solar masses. Not only that, in the lifetime of the universe, they form into binary pairs. And not only that, we've seen at least one example of a merger within the lifetime of the universe. That's all new. Those predictions, the predictions from papers that we could find that wrote about this, go from 0 to 10 to the 3 gigaparsec cube per year. And we exclude part of that because we actually saw some. The masses greater than 20, as I say, are large compared to what was known for stellar mass black holes. The progenitor is likely to be something like 60 stellar solar masses. And I think Alessandro will tell you why, but we believe that requires that you have low metallicity systems to get that. Lastly, the localization. I showed at the beginning that it was in the southern hemisphere. We don't measure it very well. We don't measure it very well, obviously, because we have 2 detectors. We basically use triangulation, the arrival in one and the other. The 2 together give a band in the sky, and the fact that they're rotated by 16 degrees from each other actually makes a little bit of difference in the amplitude between the 2, which allows us to determine it somewhat better than just a band, which is this lower part of the band that's the southern hemisphere. So that's the localization. Not very good. If we wanted to, in the future, do this with optical astronomy, we have to do it better. And this is the future. Since it's experimental, I wanted to show this. We have a 3rd detector that'll be on soon, we hope, and that's the one of our collaborators in Italy, Virgo. These banana-like shapes are shown here now, and they'll get smaller and smaller in time. And then recently, we've heard from the Indian government that they've approved for us to put an interferometer in India, which will be a collaboration between the Indian physicists who have joined LIGO and ourselves. We're furnishing the interferometer, and they're furnishing the infrastructure. And at that point, we'll be something like 2022, we'll be able to point in the sky to still not as good as you'd like, but locations that are narrow enough that we should be able to look at optical and electromagnetic counterparts for anything we see in the sky. Lastly, and I think it's my last or next to last slide, the obvious question is, what's the chance that we have more events in the data sample that we have, or the next data sample that we'll take? It's hard to predict that from one observation, obviously, But using the one observation and the range of parameters that we can use, or different ways that they might distribute themselves, we've produced the following graph. If we look at the run that we were in, which we call O1, this here, then this is the probability that we'll see more than the one event in the rest of the running. So it's 80% or 85%. So there's a good chance we'll see another one. But if we don't, it's not surprising. There's a finite chance that we won't see one in the rest of the running when we report it. So that's just a calculation. And then we can go on to what we expect. This is the volume of sensitivity that we're sensitively looking times time in this direction. That's going to increase as we improve the sensitivity. And as we go into the O2 and O3 run, we should get tens of events, as you can see, in the near future. So this kind of brings us up to 2019 or 2020 before we make any other improvements. We should, with this source, hopefully with other sources as well, be able to see many more samples. So finally, let me just conclude. We've observed gravitational waves from the merger of two stellar black holes. The detected waveforms match the predictions of general relativity for the in-spiral and merger of a pair of black holes and the ring down. And this observation is the first direct detection of gravitational waves and the first observation of black hole mergers. This is the conclusions from our PhysRev letter. I just want to point out that if you go to our website, this here, there's not just the discovery paper that you can look at, but 12 companion papers that have a lot of the information that I've presented or Alessandro will present tomorrow on everything from the tests of general relativity to the astrophysics to how we determine these parameters in detail. And lastly, if anyone would like to look at the data themselves, we've actually put it into a form where people can download the data within a certain band from this event itself and give you the tools, and you can analyze it yourself. And with that, I'll quit. Thanks.